Now? Okay. So thank you for the organizers for inviting me to participate in this nice conference. I have to say that we start to have collaboration with Sabir in the 95. That means that 30 years ago and 30 papers ago. So at that moment, probably him or myself don't expect to have so long collaboration. But for me, it was a pleasure, not only because Sabir is a great mathematician and a good collaborator, but mainly because he is a very great person, friend. And during these years, during these first 30 years, we developed some friendship relation which will continue. So thank you, Sabir. And okay, I will speak about the Poincaré series, which is, one can say, our main subject for years. And I try to first to explain a little bit of the more or less classical case of curves in the plane, just a couple of slides to situate the things. So let me take a complex curve, reduce. For each branch, we take the one valuation. So we'll have V1 up to Vr, the valuation defined by the branches of the curve. For each function, we define b of g as the vector bi of g for each valuation, which is has coefficients in the integers, mainly. And the first thing attached to this is the semigroup of values. That means you evaluate all the functions and you have some sub-semigroup of this additive semigroup. And okay, the semigroup is more or less a classical object who has the information of all the key singularity type. That means that the Puiseux pairs of each branch plus the intersection multiplicity between branches. But we want to take something more than the semigroup. And we want to collect more or less the size of the function given some value. We do this in this way. So for any vector of integers, we define this ideal. That means all the functions with value bigger or equal than k. This means that is bigger or equal in each coordinate. Okay? So this defines some multi-index filtration on the ring. And we collect the dimensions of this quotient, g of k, and we divide by j of k plus 1. That means strictly bigger than k in each coordinate. Okay, so these spaces are of finite dimension, and we collect in some Lorentz series. But here we take also negative coordinates. So with this operation, we put this kind of series inside the series with integer coefficient. This is the Poincaré series of the curve. Well, you take out infinity points. So one can consider also infinite points, but only those who are finite. Okay. Okay. So if you take some embedded resolution of the curve, you have the dual figure of the stick of the total transform of the curve gives you the dual graph, which is probably the main item of this talk, because it's the way in which one can understand more or less the things. For each divisor, we take the smooth part of this component. That means you put out all the intersection points with other components. In each of them, you can define a curveta on this component. That means that you take some curve in situ in such a way that the strict transform is smooth and transversal to this divisor. Okay, and you have m sigma is just the value of this function. These are very important elements in the semigroup and in all the talk. So one can show that the Poincaré series could be computed and give this formula, which is a formula of a Campo type. And with this formula, one has the quality of the Poincaré series with the Alexander polynomial of the link defined by the curve. Okay. So we notice that okay, here we take several branches, but if you take only one branch, the things become very easy, because one has that these spaces has only dimension 1 or 0, and is dimension 1 if and only if the element is in the semigroup. The semigroup now is a numerical semigroup, a subsemigroup of integers. Okay? So just the Poincaré series is nothing more than the characteristic series of the semigroup. That means this series in one variable. Okay, so during the talk, I don't make other situation in which we compute the Poincaré series. For example, we use other methods. We develop some kind of integration with respect to the other characteristic, which is a very powerful method to compute the Poincaré series. And also we treat a lot of different cases. But here in this talk, we will restrict just to something, in some sense, trivial case. That means only one valuation. So this is like that. And for one valuation, there is other feature of valuation which are also very close to the others, but are different. This is the divisorial valuation. Divisorial valuations is defined by one of the, if you take some modification of the plane by blow-ups, you take one irreducible component of the divisor, and you take just the valuation defined by this divisor. That means you take the pullback of any function. This is 0 along this divisor, and the order of vanishing is just the value of this. So this is also a discrete valuation, and the values are positive integers. You can take a curvette in this divisor. That means a curve defined as before. And you take this value. So this is the main graph along this talk. You have to, you will see a lot of times more or repeated with different features, but always the same. This is the dual graph of the resolution of the divisorial valuation delta or of irreducible branch. That means that the vertex are the components of the divisor, and they are linked by a edge if and only the divisors meet. So you have this figure in which you have some number of ends. That means components with valence 1, and some of them we have 3 components attached. G is the exactly number of Puiseux pairs of the branch. Okay. So for this curve, the resolution finishes here, but if you have a divisorial valuation, usually you have to blow up more times. So this divisor is the one who defines the divisorial valuation. Okay, so we take the values given by curvettas here. We play a special role in this talk. These are the key points of this. So we take this, and well, this is only to reflect what is the difference, because you see this is a discrete valuation also. That means semigroup is exactly the same as the semigroup of the branch given by some curvetta. Means there is no difference in the semigroups, but this is a good example from my point of view, because here you don't have dimension 1 always. So in principle, the divisorial valuation looks like the curve valuation, but are not the same. And the difference is not reflected in the semigroup, but is reflected in these dimensions. Here you have, for this value, you have dimension 2. So, if one want to compute the Poincaré series for this divisorial valuation, you have that this is equal to the Poincaré series of the curve multiplied by this factor. Okay, this is the difference. So that means that in the Poincaré series, it reflected really the divisorial valuation, but not in the semigroup. Give more rich information. Okay. So also the series given by the branch is computed in this way. It's very easy. It's known that the semigroup in this case is the semigroup generated by these values, which are given by curvetas in the extremes up here. Okay, and there is some relation. I don't want to explain very well why are important the relations, but are numerical relations between values in the sigmas and the values in the taux. And one have to this formula to compute the Poincaré series for the curve. It is easy and involves only the taux, which are here, and the sigmas, which are here. Okay. So now I will move to the main framework of this talk, in which we consider only one valuation, but we will consider some subfield of the complex number. I mean, you can think, for example, in the rational field or in the real field, for example. But any field is okay. We take the subalgebra of convergent functions into variables, but with coefficients k. Okay. Alternatively, you can consider this ring, the ring of formal power series. It's the same, because most part of the things depend only of a finite number of some truncations. So this is not relevant. Okay, so how to fix a valuation? We take the following situation. We take some curve, but I consider algebraic inside C2. That means that are defined by a parametrization, but here with some formal series. It's enough to take formal series here. I take a Puiseux parametrization of this branch given by this equation in such a way that this parametrization is irreducible. That means that the greatest common divisor of M and all the coefficients here is equal to 1. So with this parametrization, for any function you take in the complex ring, you can substitute, of course, and you have something which is non-zero here, some coefficient, and tau to the power b of nu of f. Okay. Okay. So this nu of f is just the value of f. That means that in this way you define a valuation in principle on the ring, but of course you can restrict the valuation to the ring of series with coefficient in k. So you have a valuation. Like before, we omit the cases of infinity, and we take only the finite values. Okay. So this is the valuation we take. So see, more or less the easiest case before, and okay, attach it to any element, any integer element. You can define these ideals as before, but now I take only functions with coefficient in k. We have the cosines, which are k-vector spaces, subspaces of C. In fact, can be embedded inside C, and you can define also the semigroup of values. Nothing new. This is only to take the values of functions on with coefficients in k, and the Poincaré series, assuming that this is defined when these quotients are finitely dimensional over k, you collect all dimensions and you have this series. I simplify this with a b t to the power b, and also of course you have this object, and you can define also the Poincaré series of the semigroup. That means that the characteristic function of the semigroup, which is more or less the semigroup is the support of the Poincaré series. So this is also important. Okay, so I recall again that if you take k equal to the complex field, all the coefficients here are 0 or 1. But this is not the case. This is not the case if you take other field. For example, if you take the real numbers, the coefficients here could be 0, 1, or 2, because are subspaces of the complex field, could be, but real subspaces. You could have only 0, 1, or 2 dimensions. But in general, the situation is much more complicated. Okay, in the real case, because I want to start to say something about the real case, which is easy to understand, well, more or less easy to understand. In the real case, so you have the situation, this repeat the size I said before, you have the semigroup, you have the characteristic series of the semigroup, and you have the Poincaré series, okay? So, the main thing is to compute. The thing that we want to do is compute the series. For this, it's usually very important to compute first the semigroup series, because it's the support of the other. That means the monomials are the same, but here you have coefficients, okay? So let me start with a fast example. I take this parametrization. It's a very easy parametrization. X is t to the 4, y is some complex non-real number generic, t to the power 6, t to the power 7. This is a very easy example. Here you see the dual graph, and here you see the resolution. That means that the divisor E, the subindex means the age. So this is the first divisor, this is the second, this is the third. Then you blow up again, and you have here the 4 and the 5. And the dual figure is like that, okay? So in the complex domain, not in the real domain, one can take curvetas here, as I explained before. This is given by, for example, this one could be given by x equal to 0, this y equal to 0, and this one could be defined by this equation. So this gives you values 4, 7, and 13. And the semigroup, the complex semigroup, is 4, 6, and 13. So now we want to compute the real semigroup. That means only take real functions and the Poincaré series, okay? So with this in mind, we made the following computation. First, these monomials give you the values. This is easy because you see here we have x, y, etc. So with x, y, and then you have these values, 4, 6, 8, 10, etc. It's easy, very easy to see that in all these cases you have dimension 1. That means the coefficient of the series is 1, the real dimension 1 for each. So here we have the first element with dimension 2. Because it's given by these two functions, 6 to the cube and y square, gives you these initial parts, 1 and alpha square, which are independent over the real. So you have dimension 2 here. This is, in the figure, is this element here. Is the first who has dimension 2. Okay? What happened with the first odd element? Because all the elements we have for the moment are even. So the first odd element, of course, is reached by a curveta index string. This one is the complex curve I take, who has value 13 for the complex case. But this is not real, this is complex. So in order to have some real one, you have to multiply by the conjugate, and you have that the value is 25. Okay? This is the first odd element on the semigroup, 25. Of course, with this, you can compute that you have 29, 31, etc. All of them with dimension 1. That means are real spaces of dimension 1. Okay, so using 12 here and these elements, one can see that the first element, which is odd and have dimension 2, is 37. And more or less this is the end of the computation. This is true always for any element bigger or equal than 41. So up to 41 is the semigroup is trivial. So summing up is not very important, the numbers, but the semigroup, the real semigroup, is given by 4, 6, and 25. This is a plain semigroup, in fact. This is the real semigroup, but this is a plain semigroup of a complex curve. For example, this complex curve gives you this semigroup. And as a consequence, one can compute this. It's an easy formula, and you have to compute this. Okay, so this is an easy example. Just to mention that in order to compute this, we need to compute the elements with dimension 2. And in the example, we see that these elements are 12 plus elements of the semigroup. So you have this formula for the Poincaré series here for this case. This is the Poincaré series of the semigroup. That means the arithmetic, pure arithmetic one, plus the elements with dimension 2. Okay? Okay, so let me explain how to work the real case out of the example. For this, we take the minimal real resolution of the curve C. I remember you that C is a complex branch, so it's not real. That means that the minimal real solution means that you have to take the minimal resolution of the real curve, which is C union complex conjugation of C, okay? In order to have the equation real.
Is it easy to know that the resolution you have chosen is minimal?
Easy, yes, because well, it's not easy if you have, for example, some real curve at the beginning, and that means that is equal to the complex conjugation, and you make the blow-ups, you don't arrive always, never you arrive to have other things. So you have to know before that the curve is real. But that's all, okay? So, okay, we take this minimal resolution. I call this the real resolution of the curve. You have the dual graph, and you have some pictures like this. Here you have the resolution of the complex curve. Okay, the classical resolution of a complex branch. And here you have a point in which you have that the complex conjugate crossing other points. So you have here some symmetry given by the conjugation, the complex conjugation between the behavior of C and the behavior of the complex conjugation of C. Okay. So from this point of view, here the group, in this case the trivial group, well, the trivial group given by the complex conjugation acts here, and the quotient is just more or less the same thing as the solution of this. So instead to use this, for practical reason, it's better to use the resolution of the branch C, which is the one I put before, but putting in evidence the point in which the complex branch separate. Okay, this is enough for this case. What means this divisor, which is the relevant thing, the most important thing? What is the meaning? Here is some divisor, and it's the first divisor such that the strict transform of C intersects in a point with non-real coordinates. Okay? So you start to make blow-ups, and in principle you have probably points with real coordinates in the divisor, no problem. This is invariant for the action of for the complex conjugation, but you arrive to some point in which you have a real complex non-real point. Okay, so then you have to blow up in two places because the curve C go by one side and the curve the complex conjugation go by the other side. Okay, so this is the And also it's related with the first non-real coefficient of the parameterization, of course. It's exactly the same, but it's near. It's near. So in particular, when you arrive to this point, after that, you have to duplicate, make blow-ups in two places at the same time, which are symmetrical, okay? But are two. Okay, so what is the situation when you take another different field, not real? Because in the case of real, more or less, it's easy to understand that you have only complex conjugation. So you take some subfield of the complex number. I take G, which is the Galois group. That means the group of automorphisms of C, which are invariant over K. And we consider the minimal G invariant resolution. That means that we make the same thing as before. I start making blow-ups. At the beginning, you have points. The curve meet only in points with coefficients in K. You can imagine, for example, rationals. But it arrives one moment in which this is not the case. So this is the first point. The rho is, I call rho for the reals, here I call rho 1. So this is the first divisor such that the strict transform of C, by the minimal modification, of course, to arrive here, intersect the divisor in a point with coordinates out of K. So you have some point with coordinates, with affine coordinates, which are not in K. Okay? So in this case, we have two possibilities. The first one is that if A is algebraic over K, you have this field K1, which is the Ka, which is a finite algebraic extension of degree these dimensions. You have also the group G1, which is the subgroup of G, which give invariant A. That means G1 is the Galois group of C over K1. And then you have that the branches of C, there are different branches in any of the conjugate points of A. So you have A is not in K. The group gives you some finite number of points because it's algebraic. And you have branches on all these points. Okay, this is the first possibility. And the second one is that A is transcendental over K. So in that case, we stop there. Why? Because if it's transcendental, you have infinite number of branches which intercept at infinite many different points. Because the automorphism of C can modify this more or less freely. Okay? So in that case, we stop there. So taking this situation, again, and make iterations, you have one of these three possibilities. Here, the first one, case one, is in the case in which you have a finite number of branches in the G orbit of C. That means you have the group G, you have the curve C, you have the conjugates of C. The group G, of course, is infinite. So in principle, you could have an infinite number of branches. But here, the case one is in case in you have finitely many, and also they are resolved on a certain step. That means that you arrive to a moment in which all the conjugates branches are resolved. So the shape of the graph is like this. This is, of course, a particular case with 6 endpoints. Here you have the first row one. You have 3 conjugates. For example, imagine you have a parameter which is the cubic root of 2, for example, over the rationals. You have 3 different. And here you have other points in which you separate in 2 components. Of course, this part is reproduced exactly in the others because you have the symmetry of the group. Okay? So as you can imagine, here you have the solution graph of C. Well, this. Okay? And this is reproduced more or less by the action of the group taking this point. So the figure we need for this case is just a resolution of a branch and also some points, row 1, row 2, up to some number, some finite number of points which we call branching points, in which simply you have the situation I explained before. Okay? So this is the resolution graph of this one. Other possibilities to this possibility is case 2, in which you could resolve the branch, but you have an infinite number of branches, of branching points. That means that the situation in which you have you found a new element which is not in the previous field is infinite. For example, if you take the parametrization in mind, you have the coefficients. If all the coefficients are algebraic over the previous one, you have some infinite situation. So you have a finite number of these guys, because these are the endpoints for a branch, analytic branch, and you have infinite number of these branching points. Okay? This is also possible. And the third case is the case in which I explained that we have some transcendental that we finish in some step. So you arrive to some point in which instead to have a finite number of conjugates, you have an infinite number of conjugates. That means you arrive to a point in which the parameter is transcendental over the field K. Okay? So in that case, we stop there. By the way, this case, one can see that the valuation restricted to the field K coincide with n times nu, where nu is the divisorial valuation defined by this guy. Okay? So here you have a valuation in the complex setting, divisorial valuation, and you have that the valuation we define is just a multiple of this. So in some sense, it's the same valuation. Okay, so what more? Let me explain the one we call more the standard main example, which is case 1. I explain you another point of view of case 1, okay? It corresponds exactly to the next situation. You have some subfield of C. Take a formal, for example, a formal series which is irreducible in this ring, the ring of power series of coefficients K. You take the quotient ring, call this a plane algebraic branch. You take the integral closure in the quotient ring of R. R is a domain, so no problem. You have the closure. This is a theorem that this closure is a discrete valuation ring. The residual field of the ring, that means the quotient of the ring divided by the maximal ideal, gives you some field that could be embedded in the complex numbers. And this is also a theorem that this is a finite algebraic extension of K. Okay, okay, so now we take this F, this equation. This equation defines a reduced algebraic curve of the complex field C. That means you have, this is reduced, this is true. So each branch of this F, that means each irreducible analytic factor of C, corresponds to a valuation, defines a valuation as I defined in the beginning. All this valuation for any branch gives you the same valuation, just this one. You restrict, when you restrict to the ring over K, gives you the same valuation. And the Poincaré series over K we defined before is just the same, of course. The valuation is the same, no problem. Okay. So the group G, in fact, in that case, you can substitute the group G by the Galois group G prime of a normal closure of K prime. You have K inside K prime. You could take the normal closure, and you take the group of Galois, the Galois group, and this is you can substitute the G by G prime. It's the same thing. In fact, there's no problem at all. So more or less the situation is exactly the case 1. Any case, any valuation in case 1 correspond to this, and vice versa. Okay. By the way, the G resolution I define is exactly the minimal resolution of the complex curve defined by F equal to 0 on the complex. Okay, okay, so one thing more to explain the theorems we have. the isotropy groups and subfields. So for any component of the divisor, one has the isotropy group of this component. That means that the group who make invariant this divisor, and for this group one has the following situation. For all vertices which are between the first one and the first branching vertex, you have always the same group, which is the previous group, the Gaussian group G. And also you have the same field, nothing is modified. If you go between two branching points are the rho J plus 1, you have that the group is stable, is exactly the same group, and the field, which is the field of the fixed field by the group Gj, is also stable. In the case 1, for all vertices after the last branching point, you have the biggest group and the biggest field. Okay, well, the smaller group and the bigger field. Okay, so you have for each branching point of this, you have some group, and you have a sequence of groups, each one inside the previous one, and a sequence of fields. And of course, you have these numbers, which are the dimension of Kj over Kj minus 1, or the index of the subgroup Gj1 over Gj. Okay, so this is the picture for this case, in which we have more or less all the data. You have here the branching points, and here, just at the branching points, you have you have the same field. Here you have a new field, bigger. You have the same field up to here, then K2, etc., up to the end. And of course, the groups will go in the opposite direction. Okay, this is the number of the degrees, and this product, the product of all these degrees, of course, gives you the degree of this big extension, K prime over K, and it's just the number of complex conjugate branches of the curves. This is the number of branches, the complex branches. Okay, so now you see, when we compute in the real case, I remember you that one have to take curvetas with real coefficients, because we are computing functions with real coefficients there. Here we have to compute curves with k coefficients. So for each divisor, we take for each component of the session divisor D, we take a curveta. That means that the smooth transversal curve to this divisor, but now define it over the field k sigma. Okay, one can take with coordinates, it's very easy to take. So this is the important thing, that this curveta is defined by over the field k. That means that you have an equation, for example, you pull down the image, you have a plane curve with an equation, and this equation could be taken with coefficients in k. Okay, so in k sigma. This is not the curveta we are interested, but we need to take all the conjugates of this. Okay, that means you take here f sigma, which has coefficients in k sigma, and you conjugate, and we have some equation of some curve coefficient in k, which is the curves we are interested. So these curves give you some value. You have a function, you have the value, you have this value. Okay, and we notice that this value is nothing more than the value of all the conjugates, of course. Okay, okay, so now first is always the computation of the semigroup Poincaré series. That means the characteristic function of the semigroup, because usually this part is more combinatorial, more arithmetical, but it's the support of the others. So this is important to understand first who is the semigroup, which is the group, and how is the series. So this situation is again the same situation as before. We take these values given by the curvetas here. I remember that when one have one complex branch, this gives you the generators, but now it's a different situation. So we take this, and the theorem says that this generates the semigroup defined over the field K. Okay? Okay, so this is more or less replies the known facts. Moreover, we have some arithmetical conditions of these elements that for people who remember more or less the combinatorial of the plane branches is not difficult to identify, but it is not relevant. That means that you have some numbers, these conditions about the generators of the semigroup, which are very relevant because they characterize the case of semigroups coming from a plane branch. That means if you have a semigroup numerical with properties like that for some appropriate numbers ni, you have that there exists a plane branch, complex plane branch with this semigroup. This is more or less the m's at the ends are more or less the pairs of Puiseux. Okay. So in particular, you see, this properties implies that the semigroup is the semigroup of values of a complex analytic curve. I remember you that you have some complex curve at the beginning generated by the small m's. Here we have big m's, which are much bigger. But again, we have that this is the semigroup of values of a complex analytic curve. It's the same case I put in the case of the reals. Why? We don't know. But it's true. That means what is the relation between this more than the pure arithmetical condition? We know the arithmetical reason of this, but we don't know any geometrical, well, in this case topological is something more complicated, but we don't know any reason for that. Simply, this is also the semigroup. Yeah, probably yes, but for the moment we haven't found you see, a deep algebraic or geometrical reason for that. Okay, so with this, it's easy to compute the Poincaré series. This is the standard for the semigroup. Is the formula we had before, but with big m's, not the small m's. Okay. So what about the Poincaré series? In the case of the Poincaré series, we again put the same graph, which is more or less the main guidance to this. And one can compute the Poincaré series over the field K, which is the Poincaré series of the semigroup, this guy, multiplied by these factors. For each branching point, you have this factor, which is the sum of a geometrical series with a ratio t to the power m rho j. So you have this formula for the computation. Okay. Well, to show this, the previous formula, the formula for the Poincaré series, involves mainly a lot of computation with the arithmetics of the one branch case. Here, one needs essentially to see the contribution of the coefficients of the dimension of curvetas in these parts. Okay, one have to compute carefully. The dimensions is not at the end. It's not complicated, but have to do is more or less different kind of reasoning. This is more geometrical and algebraic than the other one. But anyway, this is the case. Okay, in the divisorial case, I only want to say, because also I say that this infinite case is more or less the same, but here, the divisorial case, one can compute the same. So now we have some divisorial evaluation defined here. We have branching points and so and so. The semigroup is the same as the semigroup given by a curveta here. So in this, there is no difference. And this is the same computation. But for the Poincaré series, you have the Poincaré series of the curve, and just the one we define, with the same factor added that in the case of analytic case. Okay, so you can develop this and you have this. I I want to point that here, if you see to this, and in fact, this is the way to compute this. I remember that in the divisorial case, you have something which is like this with infinite number of L's. Okay, so it's like if you have here a factor in which you simply has the complete geometrical series. This is the reason, because the last factor is one over the other one. Of course, one has to prove everything there, but it's more or less the reason. Just one small remark, and I finished. The remark probably just to say that this is the semigroup of a complex curve, as I say you. So one is known that the conductor of the semigroup, that means the first element, such that everything after C is inside the semigroup. So it's computable and is given by this formula, which is a very classical formula for the curves, the computation of the conductor. So in this case, we can take this number, which is the conductor, this plus sum added, okay? This sum added. So one has that for the dimension of this of B, that means for AB, one has that this dimension is L, the product of all the small L's, for all B bigger or equal than this delta, okay? And just before, that means for delta minus 1, you have smaller strictly than L. So this number, big delta, is the place in which stabilize the dimensions. After delta, you have always L. Before, this is not the case. In fact, one has this symmetry, which in the case of plane branches is very known. If you take any pair of integers such that the sum is delta minus 1, you have that the dimensions are, the sum of the dimensions is just L. Okay? This is very known for the case L equal to 1, which is the case of a complex branch. This is the symmetry of the semigroup. But here is the same. Relating with the standard example, say case 1. There we have the ring R, which is this ring. You have the integral closure. I know that this is a valuation ring, so it's isomorphic to K prime formal power series in U. U is a parameter, uniformizing parameter of the valuation, and K prime is the residual field of the closure. And the conductor ideal between R and bar R. This is defined as the set of elements in the integral closure such that are denominators that push down the integral closure inside R. So one can compute that this conductor ideal is just this one, e to the power delta. Delta is this number. So this is nothing, not very surprising. The symmetry is not, well, it's surprising, It's a computation, the computation of delta, but the symmetry is not surprising because you see this ring R is Gorenstein because it's plane. It's not complex, but it's plane. And then the symmetry is just the characterization of the Gorenstein-ness of this condition on the ring. Okay, I stop here. Sorry, this is for other moment. The results are given in these 3 papers. 2 of them are devoted to the real case, this one and this one. And the third one is a very recent paper for the general case. So thank you for your attention, and thank you especially for collaborating with us for many years. Thank you.
Thank you very much. Any questions? In the classical case, in the case of complex numbers, there's this beautiful relation with topology of nodes, that this Poincaré series coincides with the Alexander polynomial of the node. Do you have anything in this case of subfields?
Well, I can give you something, but you see, the remark I don't make is the following, because the time If you take also in the case 1, you take all the curve with all the conjugate branches, you have a reduced complex curve. You have the Poincaré series, which is this equation, the Campo formula type, which is the Alexander polynomial. If you diagonalize, that means you make any indeterminate equal to t, you have the zeta function of this reduced curve, okay? The graph is just the same as we take before. So you have the zeta function of this reduced curve is this guy, and this guy is this formula. So you can compute this, and you have this formula. This is the Poincaré series of the semigroup multiplied by this. This is a simple computation with this. So this is the relation between the Poincaré series we have defined and the zeta function of this reduced curve. Okay, this is more or less easy and nice equation. But this is simply to compare both. Okay. Here in the zeta functions, you see you have the L's in the powers. Here you have the L in the coefficients. Okay. So in particular, with this formula, for example, using our result in mathematician Richten in the 17, is immediate to show that this determines the topology, because we prove in this paper just that the zeta determines the topology. So, for example, it's an easy consequence of this formula. And for other relations, for the moment, we don't have nothing more. I don't hear very well.
But how much the topology depends zeta function? What is the possible variance for your generating functions for a fixed homomorphism type of complement of curves, say over C just?
No, I don't know. I cannot answer you. Know. I don't know. We can't think.
Inspired by the previous talk, did you hear the situation, this P, the situation with the characteristic P?
With the?
Did you consider any analogs of this theory with the Poincaré series over characteristic P?
Yeah, could be. In fact, I'm almost sure that everything could work in characteristic P over a perfect field, because you see there is not very much differences. If you have perfect fields, that means any polynomial has different roots, not repeated roots, and so probably we can do the same thing. But we have to move our framework drastically, because we use always the things in characteristic 0 with over the corner field as a guide. So probably most part of the results are true in characteristic P, but for the moment we don't have in perspective to see what happened. Probably for someone who deals much better with curves in characteristic P or with dimension 1 rings, could be good. But I'm not sure that it works.
Thank you very much. Okay, so we have a lunch break. So let's thank the speaker again.
Thank you.
Yeah, so we have a lunch break, and we'll continue at 13.